안녕하세요. Good morning. 네, 안녕하세요. 네, 안녕하세요. Okay, so this is the first practice session. I hope everybody has downloaded the material from KLMS. If you haven't downloaded the Python notebook from KLMS, please do so now. Yeah, good morning. 네, 안녕하세요. There was no class on Monday. Tuesday? I believe you haven't checked KLMS because I've uploaded the video and the material from Tuesday. Please check KLMS um, as soon as possible. And if you haven't downloaded the material from today, please do so right now. All right, I'm going to have to start. Oh, by the way, how was your experience with the AI, the Q&A bot, the GPT that they shared the link of? Not too bad. Was very useful. Not too bad, very useful. Hmm. I'm guessing there wasn't too much too much to ask to begin with anyway, because it was just an introduction. I just asked it instead of looking through the syllabus like exams and stuff. Right. And I hope that you have cross-checked with the actual syllabus and, validated if the AI bot wasn't hallucinating or anything. In my experience, it actually was very effective. Maybe because all the questions were very straightforward and not too complicated. Like the number of the total projects and the grading policy and whatnot. Okay, I guess not a lot of people actually used the AI bot, but starting from next week, as I said, we'll be replacing that with our own invention or our own implementation. So please stay tuned. All right, so let's get on with the practice. So today, uh, as announced, we'll be going through the very basics of NumPy, and I have just 4 slides. Well, the class today we will spend time on the Python notebook. So NumPy you can think of NumPy as a MATLAB for Python. So it has a very similar syntax, the vectors, the matrices, and the tensors, how to access them, and the operations and whatnot is very similar to MATLAB. So if you've never used NumPy, but you are familiar with MATLAB, it's not going to be a big problem. And you can easily manipulate n-dimensional arrays. So vectors are like one-dimensional array. Matrices are two-dimensional arrays. And there's like three-dimensional tensors, four-dimensional tensors, and whatnot. Oh, actually, I need to. Yeah. And yep, NumPy is the foundation of modern deep learning. So all the like TensorFlow, PyTorch, and I'm guessing JAX as well. All the popular deep learning frameworks or deep learning libraries, they have a very similar syntax as NumPy when dealing with, like matrices and vectors. And actually you can like load the NumPy variables into the like, for example, like PyTorch variables. So since neural networks are just a bunch of matrix multiplications, everything runs basically on NumPy. And it integrates into, as says here, SciPy, scikit-learn, TensorFlow, PyTorch. And there is a API documentation. So if you don't know what you're doing, or if you want to look up some function names or operation names, this is the place to go. And our practice will be conducted all not just today, but all practice sessions. We will use Google Colab. So you can think of Google Colab as an online Python notebook, and you can train your models with Google's GPU or TPU for free, which is awesome. So they provide a GPU named T4. I think it's like maybe it's like way back, like maybe one or two generations before the A100. Like there were some other generations before that, right? So I think T4 is the free GPU that they provide, and you can use them for 12 hours. So it's session based. So you can train your model, or you can actually turn on the Google Colab one session for free for 12 consecutive hours. But after that, it'll actually just automatically just be shut down. So and also if you close your tab, you lose your data, or if you go over 12 hours, you also lose your data. So it's great to just, I mean, all our practice sessions, it's not going to take too much time. So 12 hours is more than enough. And if you want to save your progress or save your state, you can save them, or you can save your data in Google Drive. So you can actually connect you can link your Google Drive the directories or paths to Google Colab. So you can actually save stuff from Google Colab to Google Drive, or you can read stuff from Google Drive so that you can load your stuff from onto Colab. So that's one way to actually, like overcome the limitations of 12-hour constraint. All right, so please click this. Let's go to this colab.research.google.com. And I hope that you have all downloaded the Python notebook that I uploaded in KLMS. So let's open that. So if you open this, I think it was AI504 Numpy Python notebook. So please open them. Please open this notebook on Google Colab. And if you have trouble doing it, just let me know on the chat box. And I don't know why mine is all in Korean, but some of you should be seeing English or Korean, based on which configuration you're using. So if you click runtime, and if you click runtime configuration or whatever, you can see that you can freely use CPU, T4 GPU, or TPU version 2, but we won't be using TPU. So it's either CPU or GPU. And if you like do a paid subscription to Google Colab service, you can also use A100, which is not free, but if you pay some money. I am new here. You should be able to find the Python notebook on KLMS. All right, maybe I'll give you guys a few more seconds. All right, hope that everybody has successfully launched and booted up the Google Colab session. Is there VS Code integration for Colab? I have no idea. I'm not a VS Code user anyway. Okay, I think we have to get started. All right, so the very first line is, obviously, if you know what, as I said, the prerequisite of this course is that you have to be familiar with Python. So I'm not going to explain all the itty bitty details. So you import NumPy first, and when you execute this, you'll see that your session is being initialized. So it's like being connected to the Google Cloud, the resources. And you can see that it has T4, RAM, and disk. All right. And then these three functions are just, convenience functions that I just use to visualize or print out the matrices and vectors. So just don't worry about it. All right, the very first one. So there are a couple of stuff that we need to go through today based on. All right, actually, let me just mute everybody. Right, so there's scalars and vectors and matrices. So these are the very fundamentals of NumPy. Then tensors, defining NumPy arrays, how to define NumPy arrays, and indexing and slicing the tensors and matrices, math operations, shape manipulations, and how you can transpose or how you can shape how you can change vectors to matrices and whatnot, and broadcasting. Then there's final quiz. I mean, doesn't have anything to do with scores or grades or evaluations. It's just for you, final quiz. All right, let's go through them one by one. So the very first one is scalars, vectors, and matrices. So if you execute this and then print out all the ABCs, you'll see the A is obviously a scale. It's just 1.0, right? So NumPy np.array, it's np.array with parentheses inside. 1 is just a scalar. If you put a list inside, then it'll be a vector. If you put a nested list, so it's a list of lists, right? So there's one list here, and then there's two lists inside. So that becomes a matrix, right? I think there was a chat. Okay, never mind. Right, so this is scalar, vector, and matrices. It's very easy. So you can imagine what happens if you put a list of list of list. Then you'll have a 3D tensor. And some dimensional operation. So a.dim, a.ndim is 0. B's ndim is 1, C's ndim is 2. So you can imagine what ndim is. Ndim is just number of dimensions. So scalar values don't have any dimensions. A vector has 1 dimension. A matrix has 2 dimensions. There's rows and columns, right? So that's why ndim is 2. Shape, you'll see that you'll be using this a lot, the shape. So A's shape is, there's no shape because it's a scalar value. B's shape is a vector. So you have 3-dimensional vector. Well, actually, yeah, it's a 1-dimensional matrix or just a vector with 3 elements. So that is why the shape of B is 3. And you've seen that C is a 2x3 matrix. It has 2 rows, 3 columns. So that is why the shape has 2.3. Right? So far, so good. Very easy. So just very basics. So there's scalars, vectors, and matrices, and there's ndim and shape. So let's expand that to n-dimensional arrays. So you can see here, this is what? This is a list of, so they're like, it's 3 nestings. There are 3, it's like list of lists of lists. So this is a 3-dimensional matrix. This should be even more. You see that there are 1, 2, 3, 4. So it's a list of lists of lists of lists. It's 4-dimensional matrix, 4-dimensional array. So execute this, and you can see what happens. You execute this one. It's so it's a 3D tensor or 3D matrix, 3D array. So the number of dimensions is 3. The shape of this variable is 2x2x3. So there are how many? It's really, I mean, once you get to like 3-dimensional and 4-dimensional arrays, it's really hard to actually look at them with your own eyes and then figure out the shapes. But basically, it's 2x2x3. And as I said, this one, E, is 4-dimensional array. So there's ndim is 4, ndim 4, and shape is 2x2x2x3. So there's two of these. There's 1 and 2. And then inside there are 2 of these. 1, 2. And inside there are 3 elements. 1, 2, 3. So that's why it's 2x2x2x3, right? Very easy. So the first quiz, you can just do it on your own. So what is the shape of this? So obviously, you can check the shape of this by, let's call this f equals np dot array. Well, oops, what? You can copy this here, and then print object f dot shape and f dot shape. So the shape was 2 by 3 by 1. So everybody following along? So any difficulty so far? You can just read the shape by looking at this variable here and then just tell it with your own eyes. But the easier way is just actually define a variable and then call the f dot shape function. But you can see that the final dimension has only one element, which means that it's kind of you're just wasting dimension because this list has only one element inside. So you'd rather not just have this as a extra dimension, but it's just how it is, 2 by 3 by 1. Yep, no difficulty. Right. Okay, so moving on to defining NumPy arrays. So far what we did is we manually typed these stuff in to define arrays, right? We actually did have to type list of list with like 3 elements per list, something like that. But there are easier ways to do so, which is like one of these. This is like ones. So you can imagine what would happen. It just fills your array with ones, and the number of like the elements is defined by here 10. So you will get 10 ones. This you will get what? You'll get 10 zeros because it's zeros. It's 10 zeros, but it is shaped in a 2 by 5 matrix. So 10 zeros, but 2 by 5. So you can automatically define a 2 by 5 matrix filled with zeros. You don't have to like actually type all the zeros like this. This will be very tedious, but you can just neatly use this zeros function. Full is another function which fills your 2 by 5 matrix with a given argument, which is 5 in this case. So you have 10 fives in a shape of 2 by 5 matrix. Random is random. So you'll see here that you have a matrix or 3D tensor filled with random numbers between 0 and 1, I think, between 0 and 1. And the shape would be 2 by 3 by 4. So actually, you can search NumPy API and see what exactly is random.random. So API reference. No, here it is. Random.random. So random.random, what is this? Returns random floats in the half open interval, which is from 0 to 1, not 1 excluded. And it's just random number between 0 and 1. Well, random float number, not an integer, obviously. Right? So that's what we use just now, random.random. And you'll see the results here. This is another one. Our A range is this. So it increases it's basically 0 to 10. Well, I mean, if you put 10 here, then it'll be 0 to 10. If you put 5 here, put 5 here, then it'll be 0 to 5. 0 to 4, sorry. 0 to 4. So it's basically just counting number upwards incrementally. And since this is what? These are integers. So if you want to change them to float values, then you would have to actually change this to using as type. So you'll get 0 dot, 1 dot, 2 dot, 3 dot, and so on and so forth until 9 dot. So these are real value, float values now. And there's a reshape function. We'll get to this later, but this is just like a sneak preview. So once you have 0 to 10 up until here, you'll have okay, going back. You'll have this, but if you're not satisfied with the vector and you want to change it to a 2-dimensional matrix, then you can reshape them by adding dot reshape with 5 by 2 as an argument inside. So if you do this 5 by 2, you'll get five rows, 2 columns. If you do it, I don't know, like 1 by 10, this is also possible. Then you'll get a weird looking thing like this. Or 10 by 1 is more visually appealing, like this. So that's up to you. How you want to reshape it's up to you. But you have the product of the two values would have to be equivalent to 10. If you type 3 by 3 here, it's not going to work. It'll give you a syntax error. Well, actually a value error, sorry. So the says that you cannot reshape array of size 10 into shape 3 by 3, obviously, right? So I'm going to put this back to 2 by 5. Now quiz, create a 4 by 3 by 2 tensor filled with 0 dot to 23 dot. Let's give it a try. Please do it. You can do it right now. All right, anyone? Who's got an answer? A equal NP range 24 as type float, right? Reshape 4 by 3 by 2. Exactly. Yep. That'll do it. G equals NP range 24, G equals G reshape. Well, I mean, if you do that, then you won't get a float value. You'll just get integer values. Right? That's also so you can actually exchange the places between S type and reshape. Doesn't matter which one comes first. Oh, range 24 dot. I didn't know that would work. What happens if I do NP range 24 dot? Would that give me the float values from 0 to 23? No, it does. Didn't know that. That's interesting. Good find. Right, so I guess everybody already knows the answer. So ANP arrange dot 24.0 reshape 4 by 3 by 2. Then we can print. Then you'll get this. All right, moving on. So indexing and slicing. So indexing and slicing is you'll do a lot. You'll do a lot of these when you want to like load the training samples to your model, or you want to like manipulate the output from some layers to a next layer, and you want to change the shape, or you want to like slice them, like, or select a subset of the elements of your matrix. Like you'll do indexing and slicing a lot. So there are a lot of stuff here. Let's just go through them one by one. Well, let's. All right. So printing them out. So A range from 0 to 9 because it's 10, right? So you have 0 to 9, all integers. And what you're doing here is basically you're just accessing the first element, second element, and I'm not sure if you've seen this in MATLAB or some other math-related libraries. Like -1 is the last place. So -1 gives you 9 because 9 is the last element. So -3 will come from -1, -2, -3. So that is why you are returned with 7. So 0 is first, 1 is the second, -1 is 9, -2 is 8, -3 is 7, -4 is 6, and so on and so forth. So negative values or negative index gives you lets you access from behind. So let's just. And these are the ranges. So let's print them out. So 0 to 10, 0 colon 10 gives you all the elements, because what you're doing is you're accessing elements from the first place to the last place excluded. So 10 is the last, 10 is the last place. -1 will give you 9, right? And the same thing happens here. If you just put 0 colon and nothing inside, nothing. It used to be 10 here, right? But if you put nothing here, it'll still give you all the elements to the last element. So it'll give you the entire stuff. Same, it's like the same pattern here. If you don't put any number left side before the colon, then it'll automatically assume that you're like putting a 0 here. So it'll be the same as 0, 10, and it'll give you the same stuff. If you don't put anything left and right side of the column, then it'll automatically just assume that you're putting 0 and 10 here. So you'll get the same thing. So you see that all these give you the same results. It's just different ways to, express that you want to access from the first element to the last element. So if you put 0 to 9 here instead, for example, 0 to 9, then what would happen is that you will get one less elements because you are going from 0 to 9 minus 1, 9 being excluded. Then you'll get the final element the final element will be the 8. So, and if you put 1 here, oops, forgot to. Yeah. If you put 1 here, then you're starting from the second element, so you're excluding 0. So now you have 0 and 9 excluded. You're only getting 1 through 8. Right. So moving on. So you can assume what would happen here. You're starting from 7. You're going all the way to 5 minus 1. You're starting from 2 and then 5 minus 1. So you'll see that you're getting 7th is obviously here, right? 7, 8, 9. So you're going to the end. 7 column is nothing. 7, there's no like ending index here. So 7 column nothing is you're starting from 7 and you're going all the way. Nothing 5 means that you're starting from the 0, the first place, and then you're going all the way to 5, the fifth element. So 1, 2, 3, 4, 0, 1, 2, 3, 4, like this. 0, 1, 2, 3, 4. If you put 2 column 5, then obviously this is what you get. Now quiz. What is a -4 colon? And what is a colon -8? So -4 colon would be, right, 6, 7, 8, 9. So -4, -3 was what? -3 was 7 at the time, right here, right? So -4 would be 6, and you're starting from 6 to the end, so you'll get 6, 7, 8, 9. This is a little bit different. So you're starting from the first, but you're going all the way up to -8, and -8 is what? Anyone? Yep, 1, 2, right, exactly. So -4 was 6, 5, 4, 3, 2. So you're going all the way from 1. So I'm sorry. Well, actually, it's not 1, 2. It'll be 0, 1. Let me try it out. Print a dot -1, 8. Let me see what I. Oh, okay, sorry. Yep, it's 0, 1. Right, so hope everybody's following along. Moving on to some other, the next one. So you've seen A.10, A colon 10 here. This was actually 0, 10, 0, 10. So you've seen A colon 10, but now you're seeing one more thing here. So 2, 3, and 3. 2, 3, 3. So let's see what happens. If you put 0 and 10 and 2, one additional index here, what happens is you're skipping every other element. So you're still, the first starting place is 0, the ending place is 10, -1, and what you're doing now is you are skipping every other element. So it's now 0, 2, 4, 6, 8. So you're just skipping like 1, 3, 5, 7, 9. That's what's happening here. So the last element, the third element is how many every other element you want to access. So if you put 0, 10, 3, then you'll get 0, 3, 6, 9. And if you put 4 here, then you'll get 0, 4, 8. If you put 5 here, then you'll get 0, 5, and so on and so forth. And 2, 6, 3. So 2, 6, 3 will give you this. So you're starting from the second element, which is 2, and you're going all the way to 6, -1, which is 5, and you are skipping every 2 other elements. So it's 2, then and then you're skipping 3, so you're getting 5. So you're skipping 3 and 4, right? So this is basically that how you can control how many elements you want to skip every other time. Right. The last one. What happens if you put -1 here instead of 2? I mean, 2 was okay. 3 is now we understand what this means, right? But what happens if you put a negative value here? Then you can access the elements in the reverse order. So A is like this. Then A colon colon -1 colon colon -1. So colon means there's 0 and 10. There's 0 and 10 assumed here, but we just don't print them, and we just don't type them. So colon colon -1 gives you access to a reverse version of a reverse order of A. So it's 987654321 And if you put 5 colon, sorry, 8 colon 5 colon -1, then this is what happens. Because you're going backwards, you need to put this first, 8, and then 5 next. So you can see that the result will be 5, 7, 6. And obviously, if you don't put -1 here, if you don't put -1 here, and just say type this without the -1, then you get nothing, because you start from the 8th element and you want to say that you're saying that you want to go to the 5th element, but the order is the original, the normal order. So it doesn't work. You have to put -1 here to see this. Right, so the next one is the quiz. So create 963 using A. So A is already defined here to be A range 10. So try to get this using A. Answer A9 colon 2 colon -3. I think that would work. 0 -3. I'm not sure if that would work. Let's see if that works. Print. Oh, it does work. Interesting. Oh, because the last element is 9. Right, exactly. There's an interesting answer. -1 colon 3. Does that work? -1 colon 3. Because you're starting from 9 and then you're does this work? Yeah, I don't think this doesn't work. Because you're starting from the final element, which is 9, and you're not going reverse, or if you put -3 here, then you would probably get 963. Oh, actually you get 9630. So yeah. You'll have to put 1 here. -1, 1, -3. Then you get 963. So obviously you can see that there are a lot of different ways to get 963 out of A. So there's not just one right answer. There are a lot of different ways to express or get 963 out of it. So, always try to be creative. Right, moving on to the next one. Indexing. So far it was indexing and slicing of vector. Indexing a matrix is not that different. So you see that we have a 3x3 matrix, and then we access the 0, 0 element, which can be written as, like bracket 0, bracket 0, or actually this is way easier. So this is the C or Java style. So this is the Python style. So you open a bracket and then you just call it 0, 0. I forgot the name of this. This is not a dot. This is in Korean, this would be shimpyo. I forgot. Anyway, yeah, like 0.0. And if you want to access the first row, I'm sorry, 0, 0 is the first row, first column. This will be the second row, second column. So let's print it out. So 0, I mean, bracket 0 works, but this is easier. Just one bracket. Oh, comma, yeah, that's right. So 0, 0. And 1, 1. So if you look at this, the first row, first column is this, but the second row, second column is 4. So that is why you get 4 here, right? So the quiz is how to access the last row, how to access the second column, and how to create 8, 5 using A. You can apply what you've learned here, what you've learned in this section here. this section, and then apply it to the matrix. So how to access the last row? Let's see if just simple A -1 works. A. No, it does work. Yeah. So, but the more rigorous answer would be A -1, comma, everything. So what happens here is that as I said, this is the index for the row. This is the index for the column, and you want to get the last row. So you want to select the row, but not the column. So not the column, not the column. So you put -1 here, and then this is the place for the columns. And when you put colon, so actually this should be like 0 to 3. The real formal way to do it is 0 to 3. So this is what happens is this is the place for rows, this is the place for columns, and you're accessing all the columns from first column to the last column. But you can, as I said, we can just ignore the numbers here. If you just want to access everything, then you just put colon here. So that's why -1 that column works. And actually, you can just even ignore the column part like this. How to access the second column? So you can easily know how to access the second column, which would be everything here, all the rows here, but just second column here. Then you get, oh yeah, let me just erase this. Then you get 147. So this is 147. 147. Well, I mean, yeah, 147, second column. So how to create 85 using A? So 85 is what? We want to access this part, this 5, 8, but in a reverse order. How would you do that? How would you get A5 out of A? Uh, Two different answers, always works. 0, colon 0, colon -1, 2. That's a weird one. So colon 0, negative, like you're manipulating the rows first. Colon 0, colon -1, 2. Oh, it does work. That's interesting. So it's this last column, but you're doing something with the rows here. It's, I guess you're going reverse order. Oh, I see. So you're changing the orders of the rows, I guess. Um, Print A0, another one, right, like this. No, that also works. Wait, how does that work? Wait, 2 works, but -1 works. Huh. So what you end up with when you put this here in the row position, you get 6, 7, 8, 3, 4, 5. Right. So you're just, you're changing the order of these two, and actually you're changing the order of all the rows, and then you're accessing the first two, which is 6, 7, 8, 3, 4, 5. And when you put -1 here, oh, that's the last column. Oh, sorry. Yeah. So you're just simply accessing last column, which can either be -1 or 2. So that works. All right. I guess everybody knows how to do it. Let's just try the last one, which is a little bit peculiar. Yeah, this also works. Interesting. I don't even know what this is. 2, 2, 1. You're accessing. I think, yeah, that's accessing individual elements by this is probably like this guy, and this is probably this guy. Oh, actually, it's Yeah, let's move on. I mean, as I said, there are just probably infinite number of ways to get 5, 8 out of A. But it's good to see that everybody's following along. Right, so the next one is indexing and slicing a 3D tensor. So we've sliced like vectors, matrices. Now is our turn to slice a 3D tensor. If you play this, if you execute this, then you get 4 by 3 by 2 3D tensor, right? 4 by 3 by 2, and which looks like this. And when you access 2, 1, 0, is obviously you're just accessing this 4 by 3 by 2. So the third one being this one, and then within the third, so every single like one of these is a matrix, right? So there are 4, 1, 2, 3, 4 matrices inside, and each matrix is a 3 by 2 matrix, right? There are 3 rows, 2 columns, and you're accessing the third matrix, and within the third matrix, you're accessing the second row, first column, which is 14, right? So this is how you do it. All right, let's skip the quiz. So, I mean, these are the quizzes, but you can do it on your own time. You probably get the drift, right? So in matrix, we had row position and column position, but now we have a 3D tensor. So this is like the first dimension position, second dimension position, and the third dimension position. And the rest is exactly the same, using the using the colons, and the negative indexing, and all that. Is still the same. And there's something called conditional indexing if you execute this. So you have a matrix shaped into 3 rows and 2 columns. And when you have index like this, right? So index equals a modus, it's modus operation, right? So 2 equals 0 means that all the values that are divisible by 2 will be true, and not undivisible by 2 will be false. So 0, 2, 4 will be true, 1, 3, 5 will be false. And if you, actually, I forgot to put this here. Print a index. Let me see if this works. Yeah, this works. So if you put this index into this position here, the indexing position, then you'll get 0, 2, 4, because you're only extracting the true positions. 0, 2, 4 are true, 1, 3, 5 are falses, so you access the true positions, which is 0, 2, 4. So this is how it works. This is how conditional indexing works. So how would you create 3, 4, 5 then? Using A. I mean, obviously you would have to use conditional indexing here. So using conditional indexing, how would you? Exactly, yes. All the values here, 3, 4, 5, are greater than 2. So you want to use a condition, which is A equals greater than 2, which Changmin got right. So just as a verification, A, 2, and you will get 3, 4, 5. Well, I mean, you obviously want to print what happens if you just print this. Then you will get false, 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 which are 1, 2, 0, 1, 2, and you'll get true, true, true in 3, 4, 5. That's how it works. Next one is taking specific elements from a vector, which is, it doesn't have to be, which is super easy. You just get, so what happens here is, let's just print out A. You have A, and then you're accessing just the first, the third, and the fourth element, which is this. So you put a list inside your indexing operation. You put a list inside this. You might as well just do it like this: 0, 2, 3, and then you get 0, 2, 3, right? Or if you just do -1, -2, -3, then you get 9, 8, 7. Basically, this is it. All right, going to the next one, taking specific elements from a tensor, it's exactly the same thing. So you have a 6 by 4 matrix, and you are getting all the rows, but first column, third column, and fourth column. So that is why you have all the rows. I mean, this is the original A, but you have all the rows, Well, you have first column here, third column here, and fourth column here. So that is what's happening here. This would be the opposite. This would be you're accessing the first, the third, the fourth rows, but all the columns. So that is why you have first, third, fourth rows here, and all the four columns, or all the four columns. Right. So you can try this, try these at your own leisure. It's basically just selecting specific rows and specific columns. And ellipses, this is kind of like a convenience function. So what's happening here is that you have a very large shaped, very weirdly shaped matrix, which is 2 by 3 by 2 by 2 by 4 by -1. Sorry, so the -1, if you put -1 in the for example, so if you divide 288 by 2 by 3 by 2 to 4, then there should be like some value here, which is what actually? What's 2 times 3 times 2 times 2 times 4? It's 96. So, right. So there should be 3 here, actually. There should be 3 here, because if you multiply all these numbers, then you'll get 288. But, it's just tedious to do the actual calculation. So you only want to define all the 2, 3, 2, 2, 4s here, and then let the machine just figure out the last number, which would be 3. So that is what -1 means here. So you have how many dimensions? You have 6-dimensional array, 6-dimensional and n-dimensional array, and you have things that looks like this. And what you're doing is you want to get the first, I don't even know what this is. This is not a row, this is not like just first element along the first axis. I'm sorry, the second element from the first axis, and the third element from the last axis, and you want to get all the things in between. But this is tedious, so what you do is you just put ... here, ... That is what ellipsis is, and you get the same results. So this is the plane indexing. This is the ellipsis indexing, and you get the same thing. So just whenever you want to just, don't want to type all the colons, then just type ... Right, so moving on to the math operations. So far so good. Any question? Right, then move on. So math operations, these are the basic math operations. You have a matrix. Well, and these two are also matrices. Let's just run this. You have two matrices, 0, 1, 2, 3, 4, 5, and 1, 1, 1, 1, 1. And if you add these two, these are two equally shaped matrices, right? So this is a 3 by 2 matrix. This is also a 3 by 2 matrix. So you can add them, subtract them, multiply them and divide them, and you'll get this. You'll get this. And note that this is a integer matrix, and this is a float matrix. So this is an integer. These are all floats. But if you do math operations between the two, then you'll get just float results like this. Automatically, this will be converted to a float matrix along the way. Unary operations, these are binary operations. So you add them, negatives, subtract them. These are all binary. But unary operations are, for example, like sum or mean or max or min, right? So you have a matrix, 3 by 2. If you just simply call the sum operation, a.sum, then you'll just sum up all the elements inside. So you get 15. But you can specify along which axis you want to sum. So if it's along the first axis, 0 is the first axis. If you want to add row-wise, then you get 6 and 9. So 0, 2, 4 is 6. 1, 3, 5 is 9. So you get 6, 9. If you add elements along the column-wise, like along the second axis, the column-wise, then you get 1, 5, 9. So 1, 5, 9. So that is why you get 1, 5, 9. And if you call the mean operation, you just average all the elements. So average mean like 15 divided by 6 would give you 2.5. And max is obviously the maximum element, and min is the minimum element, the smallest element. And you can also do this along you can just also put axis here. Axis equals 0, x equals 0, then you get these. So you average along the first axis, which is the row. So this would be the row-wise averaging. Max is, you also do max along the row, along the first axis, which is the row-wise. So row-wise maxing is, out of all these, 4 is the largest. Out of all these, 5 is the largest. So you get 4, 5. So you'll use a lot. You'll use this a lot. Quiz, given a NP range reshape 2, 3, 4, 5, 3, 3, 2, 3, 4, what is the mean of the sum with respect to the last dimension? So, well, I mean, I think we're running out of time. So you can do this on your own time. So we have to spend some time on the final quiz. So let's just skip some of the quizzes along the way. Dot product. So this is important, actually. So you have two vectors and you want to do a dot product or inner product between the two vectors, then this is what happens. You have 0, 1, 2 and 1, 1, 1. And if you want to do a dot product between the two, you just call np dot a comma b, and that's it. So this will give you a dot product of the two vectors a and b, so which is 3. So 0, 1, 0, 1, 1, 1, 2, 1, 2. So add them all up is 3. So that's the dot product. Dot product between matrices also can be used like this, like np dot, or there's a this is what this is a at, like a at b. So these two will give you the same results. So you have one matrix 3 by 2, another matrix 2 by 3. So if you dot product them, you'll get 3 by 3, right? So this is a 3 by 3 matrix, but if you get the same thing with this operation, this operand, this at. And actually, you should be more familiar with at more than dot if you go even higher dimension. So when you have 3D matrices or 3D tensors like this, so one is 4 by 3 by 2, another is 4 by 2 by 3, then let's first of all, before you actually look at the results, let's imagine what would happen when you do a dot product between the two. If you do a dot product between A matrix, which is 4 by 3 by 2, B matrix, which is 4 by 2 by 3, what would happen if you do a dot product between the two? Think for a second, So what happens between a dot product between 3 by 2 and 2 by 3 matrix? You get 3 by 3 matrix, right? Here you have 4 by 3 by 2, 4 by 2 by 3. So you would imagine that let's just keep the first axis intact and let's just, play with the second and third, 3 by 2 and 2 by 3. And if you do a dot product between the two, then you'll get 4 by 3 by 3, because 4 by 3 by 2, 4 by 2 by 3, you leave the first elements alone, then you get 3 by 2, 2 by 3 matrix dot producted or inner producted. So 3 by 3, so you will get 4 by 3 by 3. So that is one way to do it. So that if you want to do that, if you want to get 4 by 3 by 3 out of a dot product between these two, then you need to call this function, this a at b, because np dot ab will give you a weird shape like this. So only a at b will give you 4 by 3 by 3. So the reason that I showing you this at operation is because usually when we have deep learning like algorithm or learning process going on, the first element is the batch element. So the individual training samples will be the ones coming after the first element. For example, in this case, you could imagine that your training samples are 2 by 3 matrices and you have four elements in your mini batch. So in that case, you want to leave the first mini batch, the batch axis intact, and only want to do a dot product with the remaining axes, right? So that is when you can use the at operation or the at operand. If you use a dot b between 4 by 3 by 2 and 4 by 2 by 3, you will get a weird shape like this, 4 by 3 by 4 by 3, which I assume, which I imagine is happening is there is 2 here and there's 2 here. So something is happening along these twos, and they're just somehow merged or canceled out, and you get 4 by 3 by 4 by 3. So I don't think you'll be using np dot for higher dimension matrices, like third order, fourth order, like three-dimensional, four-dimensional arrays. I don't think you will rarely use like np dot. You'll most likely use a at b. So keep this in mind. So when you're dealing with matrices, both are okay. But when you're dealing with 3D tensors, you have to be really sure. You have to know what you really want to do. If it's this or this or this, right? What happens if the dimension is more than 4? It's that's an interesting question. Hmm. Let's try it out then. 4 by if you multiply 84, 48, 1 is 4 by 2 by, let's see, 4 by 2 by, let's just first play with 4 by 2 by 2 by 3 and see what happens. So no value error. So you get 4 by 2 by 3 by 3. Yeah. So the AND operation will give you, like, as long as the first two are the same, then it'll happily play along with the remaining two axes, then do the dot product between the two. So the 4 and 2 will remain intact, and the 3, you can see why there's 3 by 3 here. I don't exactly know what's happening here. 4 by 2 by 3 by 4, 2, 3, 4, 2, 3. How does this happen? 4, 2, 3, 4, 2, 3. I think something is happening along the last axis and the second axis here. So that is why you get 4, 4, 2, 3, 4, 2, 3. Like if these two cancel out, then you get 4, 2, 3 and 4, 2, 3, right? So if you're interested in this, you can just go to this website and just call np. Oh, actually, you should call numpy. Yep, numpy. And you can see all the rules about how it's supposed to run. So, for example, if if A is an n-dimensional array and B is a one-dimensional array, the sum, yada yada yada. If A is an n-dimensional array, B is an m-dimensional array, where n and m are both larger than 2. It is a sum product over the last axis of A and second to last axis of B. So last axis of A and second to last is 2. So I guess these two are being canceled out. So if you're interested, just go to numpy and read the specifications. All right, moving on. So we've finished with the math operations. We're actually not. Oh, okay. So we only have 2 more things to go. Shape manipulations, as I said. So we're gonna see a lot of reshapes. So you first start with 24, so 0 to 23, all incremental, increasing, and you reshape them to 2 by 3 by 4. So that is why you get 2 by 2 matrices, where each matrix is 3 by 4 matrix, 3 by 4 matrix. If you reshape this into 6 by 4, this would work, because 6 by 4, if you multiply them together, you get 24. So 2 times 3 by 3 times 4 is 24. 6 times 4 is 24. And as I said, -1 lets the machine figure out what this value should be. And in this case, this should be 4, because this is 6. So this is just has to be 4 to satisfy the product between the two being 24, right? So you get this. What would happen if we do dA reshape 6 for -1? What would happen? You can try it out right now. Print A dot reshape 6 by 4 by -1. So obviously 6 by 4 by -1. 6 by 4 already satisfied that the product between the two would be 24. So I guess this should be 1. This has to be 1. There are no other ways. So you would get this, redundant single element lists in the innermost nesting. So this is what you get. 6 by 4 by -1. Adding on extra dimensions. So this is a trick that I used a lot when I was implementing all the like PyTorch models or TensorFlow models. Is when you want to add a extra dimension, you can just use none. So for example, if your original vector looks like this, like 0, 1, 2, and you want to add extra dimension in the innermost nesting, then you put none here, then you get 3 by 1 tensor. 3 by 1 matrix. Right. So when you shape, you will get 3 by 1. 3 by 1. Quiz: how to make a NP134 into shape 3114 using reshape and none. Well, I guess you can do it without actually using the reshape. Because if A is np dot ones 3 by 4, and you want to get 3114 out of it, then B equals A, nothing, none, none, nothing. I mean, everything, not nothing, everything. So then print B shape would be 3114, right? This is it. If you actually print this, let's see what happens. It would have a just bunch of weird, redundancies inside. 3 by 1. So there's 3 elements like this. 3 elements. 1, 2, 3. And inside there's just one element. And inside there's again just one element. And inside there are 4 elements. So that is why it's 3 by 1 by 1 by 4. Stacks and concatenations. So this is you'll use this a lot. So when you have ones and zeros, like 3 by 2 ones, 3 by 2 zeros, 3 by 2 zeros. And when you do a V stack, which is a vertical stack, so you stack A and B vertically, then what happens is this. So verticals, NP V stack A, comma B, right? Then you get A first and B second. If you do B dot A, then the order would be reversed. If you do horizontal stack, H stack, A and B, then you would obviously get this. So you have ones coming first, which is the A, and you have B here. You can do this more than 2 times. A and B and A horizontally, then you will get this, right? 1, 0, 1. So this would be A, B, and A. So that's the H stack. And you can actually do all of these just using concatenate operation. So np.concatenate, and if you do A and B, and you have to specify along which axis you want to concatenate. So if you concatenate along the first axis, which is the row axis, then you get the same effect as V stack, vertical stack. So you can see V stack and concat axis 0 is exactly the same thing. If you specify the axis to be 1, the second axis, the column axis, then you get this, which is exactly the same as H stack. And note that V stacks and H stacks works with matrices, but if you have like higher dimensional like tensors, it's really, I'm not sure if it's possible or if it's tricky, but you're better off using concatenate because you can specify along which axis you want to basically concatenate, right? Yeah, there's a quiz. Would concatenating 2 tensors whose shapes are 4 by 3 by 2 and 5 by 4 by 2 on axis 2, the last axis, would this work? So concatenating these 2 matrices along the last axis, would that work? Would it work? No, and the reason being why? Yeah, remaining dimension does not mesh, exactly. So if you wanted to do that, then if I'm right, if it was 5 by 4 by 3, then this would work, right? Am I right? Students, who knows this better than I do? The important thing is that the remaining dimension needs to match. And the one that we're concatenating along doesn't have to match because we're concatenating them, right? You guys are not sure? We can just try it out then. A is NP ones 5 by 4 by 2. B is NP ones 5 by 4 by 3, and then NP concatenate A, B, axis 2. Let's see if this works. Oh, it doesn't work. Let me see why it doesn't work. Oh, okay, there's a typo here. Concatenate. Concatenate. Yep, this works. So as I said, so it doesn't matter whether the target axis matches or not because you're actually concatenating. Oh, sorry. Could you give me a second? All right, sorry about that. Right, as I was saying, the important thing is that the target axis doesn't have to match, but the remaining axis need to match. So that's how you do concatenate. Right, moving on. So the matrix, this is transpose, simple transpose. If you put dot T, the capital T, then you get a transpose of a matrix. But this wouldn't work if you're handling, n-dimensional arrays. So in n-dimensional array, when you want to transpose, you have to use a function called np.transpose. So see what happens here. You have a three-dimensional tensor, which is 4 by 3 by 2, and you want to swap. Basically, transpose is swapping between columns and rows in matrices, right? So this is basically like, this used to be rows and this used to be columns, but now you have instead, now this is a row and this is a column, right? So you're swapping between rows and columns. So sorry, give me a second. Right. So as I was saying, when you're basically the essence of transpose is you're swapping between two axes. So if you want to do that with n-dimensional arrays, then you just use transpose function, and then you'll see what happens here. So NP, the A is a 4 by 3 by 2 matrix, and if you swap axis 1 and 2, so you have transpose and 0, 2, 1, which means that you want your the first axis intact, and you are swapping between the second and the third axes. So that is why you get this. Could you give me a second? Right. So as I was saying, you are swapping between the first and well, I mean, axis 1 and 2 is the second and the third axis, right? So this is what happens. You get, it used to be 4 by 3 by 2, 4 by 3 by 2, but now you have 4 by 2 by 3 because you've swapped between the second and the third axis. If you do this instead, if you do 0, 1, 0, 2, then what happens is 1, 0, 2 is you're getting the second axis in the first axis in the second place, and you're leaving the third axis intact. So you get 3 by 4 by 2. It used to be 4 by 3 by 2, but if you swap like this, then you get what? You get 3 by 4 by 2. So you can, using the transpose function, you can just swap any axis as you want. It could be 0, 2, 1, it could be 0, 1, 2, it could be 2, 0, 1, 2, 1, 0, 1, whatever you want, right? So you can just swap axis as you feel like it. And this actually works not just on n-dimensional arrays, but also on matrices. So in matrices, you have two options. You can either do dot T or you can just use transpose. All right, the final one is the broadcasting. So we'll have some time for final quiz. So broadcasting is a interesting concept that actually makes your life very way easier than it has to be. So what happens here? Let's see. So you have one element, one A, which A is a vector. Actually, we need to print. Oh, okay. So yeah, A is like this. B is just 2. B is 2. So A is a vector. B is a scalar, right? And when you add these two, it shouldn't work because the dimensions don't match. A is a one-dimensional vector with 3 elements. B is a dimensionless scalar. So if you try to do binary operations between the two, technically it shouldn't work, but it actually does work. If you look at A plus B, A minus B, A multiplied B, A divided by B, it all works. And the reason is that the B is actually being broadcasted into a vector. So B is a scalar, but when you call functions like these, then internally B will be transformed into a vector with 2, 2, 2. Basically, it will be transformed into, oops, what is it? NP like 2 dot 2 dot 2 dot like this. So if you actually do this, then the results will be exactly, I forgot already. Results will be exactly the same. So internally, B used to be 2 dot, so 2, just a float value, 2 scalar value. But internally, it will be transformed into this along the way. So that is broadcasting. So this also works with, matrices and higher dimensional matrices and whatnot. So if you have A that looks like this, and B, so A is a matrix, B is a vector. So B is one dimension less than A. And if you do a addition between the two, B will be broadcasted into what? So if you look at the results here, B was broadcasted into 1, 2. Let's see. Like this. 1, 2, 1, 2, 1, 2, 1, 1, 2, 2, like this. So B was automatically broadcasted to match the dimension of A, which is higher dimension than B. So broadcasting is basically if you do something with two variables, where one variable has a higher dimension than the other, then the other one, in here this would be B, in the other variable will be broadcasted into a higher dimension to match the dimension between the two, and then do the math operation between the two. So that's the basic concept. Quiz. There's a quiz here. What would happen if B were np.arrange 2 reshape 2, 1? Interesting question, right? What would happen if B was not just a scalar value? Sorry, not scalar. B, what if B was not a vector, but actually, if you do it like this, then B would become a matrix, right? So already there's an answer. In the first case, it would result in a 2 by 1 column vector, thus resulting into broadcasting error. I would think so. Let's see what happens. B is now B dot reshape 2 by 1, right? Oops. And if you print B, yep, so 2 by 1. So 2 by 1. And then if you try to do A plus B print, what happens? There's a value error because, as Namo said, the dimensions don't match. So it has to, if it was okay when it was just a two-dimensional vector, when it was, sorry, it was a one-dimensional array with 2 elements, which is a vector, right? It was okay when it was a vector because you could easily broadcast it into 1, 2, 1, 2, 1, 2, right? 3 by 2 matrix. But if it's already 2 by 1, then it wouldn't work. If it was 1 by 2, this could work because, it means that this is a matrix with 1 row and 2 columns. So let's see what happens. If it was 1 by 2, it does work. Yeah, exactly, like Lamho said, results in a 1 by 2 row vector leading to a successful broadcasting result. Exactly. So you can see that it is successfully broadcasted. So you can see what's happening here. Yeah. I mean, you'll have to spend some time doing a lot of the playing around with the matrices and vectors and dimensional arrays to really figure out what really happens with the broadcasting. Tensor matrices, this is the same thing. If you have a 2 by 3 by 2 tensor and a 3 by 2 matrix, and if you add the two, then this would be okay because this 3 by 2 matrix will be broadcasted into let's see. This will be broadcasted into a tensor with 2 of these matrices inside. So it will be 2 by 3 by 2 again. So you can see that A plus B, what happens is you add this here to here for once, and you add this to here again. And that's how you get these values, right? So what's happening is basically this is being transformed into a 1 by 3 by 1 by 3, 2 by 3 by 2 matrix. And if B was actually a two-dimensional vector, if B was a NP, if B was like B reshape Actually, it wouldn't work. So if B was like np dot array uh 1, 2, like this. If this was B, then it would still work because the last axis matches because this is a two-dimensional vector and there's two at the last axis. So the B just needs to be broadcasted 6 times, 2 times 3, 6 times, and this would work, right? So that's how broadcasting works. Right? Well, I mean, might as well just give it a try too. See what happens. Works like a charm. So B was 1, 2. So 1, 2 was added here, 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 6 times. But if B was 3, probably wouldn't work. Yeah, value error, because 3 doesn't match the last element. So the important thing is the last axis needs to match. Okay, so far, so good. I hope that everybody's following along. We just have the one final quiz left. This is a little bit convoluted. I think there was some ambiguity somewhere. Uh, yeah, this should be okay. So try to solve this quiz, and I'll give you a test case. Read the specs, and try to, define the function foo here, and then, if once I give you a test case, you can test it out. So this will be your test case. Put m, I mean, define m like this and w like that, and then when you plug those values in, you should get a specific value, which is the answer that I know. I'll give you guys maybe like 5 to 10 minutes. If you have any questions regarding the material that we covered so far today, you can ask them now. Question. Will the practice content, the notebooks and associated slides be more or less the same as last year if one wants to look into subsequent lectures to progress? Will there be a risk of missing things that have been edited? No, it'll be more or less the same. Yep. All right. Anybody has solved the problem? Just, post your answer with the given M and W, the test cases. 2.0 point something ish. Three same answers. I think that is the correct answer. Anyone who got a different answer? Same answer here. Okay, cool. Yeah. I think everybody's following along. Great, great. So basically this requires a bunch of, like indexing and reshaping and whatnot. And well, there should be like one final mean operation. Mean operation. Oh, also, yeah, the skipping because there's odd numbered and even numbers. So you should. Can one of you who got the answer post your solution to the chat box? No, that's even shorter than mine. Only 4 lines. M shape. You do the H stack. Yeah, I think that looks okay. Again, as we've seen many, many times, there's not one answer to this question. Obviously, mine is way different than Namo's solution. So don't worry if you didn't, if your solution doesn't look exactly like Namo's. It's whatever works, it works. Okay, so I think we can end the class today. one quick question. What on the slides of the first lecture, there is a page describing the first assignment. Does assignment mean no, it does not. It's not even assignment. It's just telling you to install Anaconda if you want to. All as I said, all our practice sessions will be conducted on Google Colab, like today. So you don't really need to install Anaconda, but if you want to do some local experiment using your own laptop or your server, you should, you know, Anaconda is a pretty good place to start. When will the details of project one be? It'll be announced at the week of the project, which is I think the midterm week. And when will 24 hours start to count in the week? It will start at like either Tuesday or Thursday. Yeah, we haven't figured out all the details of project one because this year, starting from this semester, this course has changed to the pass or fail. Last year it was letter grade, so we had to, make the projects like a little bit challenging to distinguish between different grades. But now this is a pass or fail, so we don't need to do that. It's just so we're trying to dial down the difficulty of projects a little bit. Right, any other questions? Uh, Unfortunately, next week I have a business trip to Beijing, Microsoft Research Asia. So we won't be able to have a online theory session next week on Tuesday. So Thursday, it's okay. Thursday, a TA will be doing the practice session, but the Tuesday, I won't be able to do the class. So I'll give you guys link to the last year's class number 2, and then you can watch the video, and then if you have any questions, you can. Well, actually, I can have if you guys let's talk it up on KLMS. If you guys want, I can have a like extra session at an evening or some other time to get a question answer. I mean, have a Q&A session just for class 2 because you wouldn't have otherwise it wouldn't be fair to you that you have to talk to the AI bot. So if you guys want, I can have a separate question answer session. It will be like a flip learning, but on a in a different hour. All right, any other questions? Yeah, this year we have a lot of like off days because I think October 1st is also an off day. 국군의 날 it's like a soldier's day, I think. And starting from this year, I think the government has decided to have the soldier's day as an off day, a holiday. And that turns out to be, I think, Tuesday sometime. All right. If there are no other questions, I'll see you guys the week after next week, or actually some other time in next week if we decide to have the Q&A session. All right. Thank you guys. Have a good rest of the day. Thank you. Bye bye. 네, 감사합니다. All right. Thank you. 네, 감사합니다. Thank you. Bye bye.